I'm Dan, and I'm going to be presenting our work about the semantics of shared memory in Intel CPU FPGA systems. So let's start with an introduction. CPUs are great because they have a fixed set of instructions, making them easy to use. On the other hand, FPGAs have configurable logic that can be used for more specialized tasks. The FPGA only needs to power the circuitry that is needed to perform the computation of interest. Hence, all circuitry that is not needed is eliminated, meaning that a lot less power is utilized. Usually, designers have to choose one or another depending on their application. But recently, systems that combine both a CPU and programmable hardware have started to become widespread. Programmers can nowadays spread their computation between a CPU and an FPGA such that both components run in parallel. Applications usually utilize the CPU to handle general computing, while the FPGA logic comes into play for more specialized custom tasks. Intel is one competitor on this market, and it has already released its third generations of systems that combine both a CPU and an FPGA. Our work aims to answer fundamental questions about how to reason about programs that are split between the CPU and the FPGA. So we know that all architectures deploy some sort of optimization, which can cause weak memory behaviors. One such optimization is present in x86 architectures, where we have a write buffer between the CPU thread and the shared memory. In this case, the thread can read from the main memory or from its own write buffer. We want to understand heterogeneous systems such as the Intel CPU FPGA-1. Therefore, we want to see what kind of reorderings can affect the FPGA operations. Here we have the Intel Xeon plus Aria FPGA. The FPGA is connected to the CPU main memory via multiple channels. Under the hood, these channels are PCI Express or QPI links. We will later see that these channels are responsible for some very interesting behaviors that the programmer must take into account. The FPGA has some very unique behaviors, so let's look at an example of coherency. If we send a write request to an address, then send a read request to the same address, we have no guarantee of receiving the new value. We can disallow the read of old values in two ways. The first option is to use the same channel for the write request and the read request, but only issue the read request after we have received a response from the previous write request. The second option is to use whatever channel we want for the write request and the read request, but to also issue a fence between these two operations. A fence guarantees that all previous write requests have reached the main memory. Now things get a lot more interesting when we add a CPU thread in the mix. So let's look at an example of message passing, where a thread writes some data, then sets a flag that the data has finished writing, and the other thread first checks the flag, and if the flag is set, expects to read the new data. So on the left, we have an example where the FPGA is the producer and the CPU is the consumer. To disallow write-write reorderings on the FPGA side, we need to issue a fence request between the two writes. On the CPU side, things are a lot more simple. We don't need to add any synchronization primitives if we use an x86 systems. If we were to use a different systems, other synchronization operations might be required. In the figure to the right, we have the mirror case where the FPGA is now the consumer. Unlike the CPU consumer, the FPGA does allow read-read reorderings if synchronization is not used. In this case, the FPGA instruction stream simply needs to wait for the read response regardless of the channels. The CPU side is similar to the previous message passing variant, since write-write reorderings are preserved in TSO. We can see here the difference between CPU operations and FPGA operations. On the CPU side, we have simple writes, reads, and fences, But on the FPGA sides, these operations are broken down into requests and responses, and we also need to specify the channel on which the operations are gonna be issued. So now let's take a look at the memory model that we have developed for this heterogeneous CPU FPGA system. Here we have the shared memory that both the CPU threads and the FPGA threads want to access. We already know the memory model of an x86 system. We know that writes go through a write buffer before they hit main memory, and that threads can read directly from the shared memory or from their own write buffer. But now we also have these FPGA operations and want to know how they are going to reach main memory. The first thing to take into account is that these FPGA operations can go through separate channels on their way to the main memory and back from the main memory. The second thing to take into account is that writes and reads can get reordered. We have modeled this reordering using write request pools and read request pools. And thus, we have the operational model of the heterogeneous CPU FPGA systems. So we wrote down the operational semantics for the previously described model by using the Intel manual. We implemented litmus tests where the manual was not clear, and finally we mechanized the operational model in CBMC and validated with all the traces described in the manual. We have also created an axiomatic model of the system. We explain all the axioms in the paper, and here I won't go into details about them. These axioms are similarly implemented in Alloy and validated using the manual traces. Now that we have the operational model and the axiomatic model, we want to see if these models match each other and if they match the actual hardware. We start from the axiomatic model implemented in Alloy by generating a large amount of traces. We then execute all these traces on the operational model implemented in CBMC. Whenever there is any discrepancy, we find out where the problem is, fix it, and then rerun all the traces. After there are no more discrepancies, we want to see if these models actually match the actual hardware. So Alloy can generate a large amount of tests that can be run on the actual hardware. The challenge here is that while compiling the CPU part takes just a few seconds, synthesizing the FPGA part can take a few hours. Running a single test is limited by the speed of synthesizing for the FPGA. For this reason, we write a very simple softcore processor on the FPGA that is able to interpret basic litmus tests. The processor only needs to be synthesized once. So now, instead of recompiling a litmus test for the FPGA every time, we just send it a sequence of instructions to be processed. So in this case, Alloy generates a test and sends it to the CPU. The CPU sends the corresponding stream of instructions to the FPGA. Then both the CPU and the FPGA execute the litmus test. Now, there is one more thing to take into account here. The FPGA cannot directly display the results, or at least it cannot easily display the results. For these reasons, we send the results back to the CPU for them to be displayed. Here we have a basic representation of the softcore processor on the FPGA. The softcore processor starts in the idle state, and then when it receives a signal from the CPU, it first checks the program counter, then fetches the corresponding instruction and decodes it, and depending on the instruction, it either sends a request or it waits for the corresponding response. Afterwards, it increments the program counter, and then if there are no more instructions to be executed, it writes the result back to the CPU. Now there is another challenge that we face here. Alloy generates a lot of traces that require quite unique response sequences. We cannot directly control how we are going to receive these responses. It can happen quite often that we are not able to reproduce the test. It has been shown that stress testing can expose a lot of weak behaviors. For this reason, we introduce a bit of randomness to our experiments. We have this parameterizable stress request that we send alongside the actual test. The stress helps us uncover some of these interesting behaviors. Now that we have a model of our system, we want to see how this model affects actual applications. We noticed in the literature that for some applications, it is common for the CPU to communicate with the FPGA via a producer-consumer queue. Therefore, we implement such queues, one from the FPGA to the CPU and another from the CPU to the FPGA. Using our model, we can see that there are two ways to implement such queues. The first option is using a single channel and waiting for responses, and the second option is using multiple channels and inserting fences at the correct spots. We verify the basic queue operations in CPMC using our previously described model. We have tested these versions of the queues on the actual hardware. Both these queues are running in the presence of stress. What we see here is that as we send more elements through the queue on the x-axis, the time taken to do that on the y-axis increases linearly. The line for the version with multiple channels and fences is lower. This suggests that the version is more efficient. Both versions of the queue receive all elements correctly, even in the presence of stress. Afterwards, we run the same experiment, but we eliminate all synchronization primitives. We want to see if synchronization matters and if our model is not too conservative. Similarly, we also have stress in our experiment. The red line represents the version of the queue without any synchronization primitives. The number under the line represents the percentage of elements lost. We can see that although the version without synchronization is faster, it does lose about 10% of the elements in the case when the FPGA is enqueuing. Depending on the application, the programmer can decide if he can tolerate the percentage of elements lost. Now, in conclusion, we have provided formal semantics for the CPU FPGA systems, both in operational form and in axiomatic form, and we have mechanized both these semantics. And we have also provided a software processor for efficiently running litmus tests on such a heterogeneous systems. We have validated our models using cross-checking and by actually running on the actual hardware. And we have provided two versions of a popular producer-consumer synchronization primitive. Thank you for your attention.